With that in mind, one of the most powerful uses of dictionaries is the ability to have multiple dictionaries with the same keys but different values. This data structure is a low overhead version of object-oriented programming, which we'll cover in the next unit. So to start, let's convert that address book code to work with dictionaries. Instead of defining a tuple for each person in our address book, we're now defining a dictionary. Each of their dictionaries has 3 keys: address, phone, and email, and has corresponding different values for those 3 keys. So just like before, we can still access all of David's information by putting the key David into address book. But now to access Dana's phone number, we don't have to know that the phone number is located at index 1 in a tuple. We instead just have to call it by its name. Look up the value for the key phone in the dictionary that corresponds to the key Dana in the dictionary that is the address book. This code runs by first replacing address book sub Dana, or address book with the key Dana, with that actual dictionary. So that comes here. Once we have that dictionary instead, we look for a key phone and return the value of it. And sure enough, that key is here, and so the value is returned. And that's why we see that phone number in our output. Our code got a little bit longer, but that's okay, because what we gained is the ability to refer to these individual values by keys instead of by indices. Don't underestimate that trade-off. It might seem easy to remember this for only 3 values, but imagine if you were dealing with several different dictionaries with several different types of data, or with one dictionary with something like 20 different fields. With lists, you would need to remember the index for each individual type of data, as well as remember to declare them in the right order. With dictionaries, you merely need to remember the name that goes with each kind of data. And it's much easier to remember that the key phone corresponds to phone numbers than it is to remember that the phone numbers belong at index 12 or something like that. It's similar to how you would remember variable names. Now note that this merely implements something resembling object-oriented programming in the simplest terms. Real object-oriented programming has a lot of additional benefits that we'll cover soon. But still, this approach gives a glimpse at the power of object-oriented programming, as well as a way to realize some of its benefits with relatively low overhead. So to show this off, let's take one more example. Imagine we're teaching a class with 5 students and we gave a multiple choice test with 5 questions. Now we want to grade the test. We could do that with dictionaries. On line 1, we define a dictionary that represents the answer key. On line 3, we create an empty dictionary of students, and on lines 4, 5, and 6, we put in each student's answers to the test. The key 1 is the student's answer to the question number 1, and the value corresponding to key 1 is their answer to that particular question. So for example, here we see that David put B for number 2, Tara put B for number 2, and Lugos put C for number 2. To grade it, we now would iterate over each student answers pair in our students dictionary. So our keys were student names, and our answers were dictionaries made of key value pairs, where the keys were question numbers and the values were answers. Each student has a different such dictionary, but the important thing is that the keys among all those dictionaries are the same. Each student has 1, 2, 3, 4, and 5 as their keys, and those keys also match the keys from our answer key. On the first iteration of this outer loop, David is loaded as the key, and David's dictionary of answers is loaded as the value, now accessible under the variable name answers. So answers now holds the dictionary corresponding to David's answers to the test. For each student, we start the grade at 0 because we haven't marked them correct for anything yet. And then we run an inner loop, iterating over each individual key value pair inside of each student's answer dictionary. For each one, we check to see whether the value corresponding to that key value pair equals the value associated with the same key from the answer key. So on our first iteration through the inner loop, we're dealing with David's answers, and the first key value pair has a key of 1 and an answer of A. So our value for the variable question is currently 1, and our answer is A. It then checks to see if answer for David A equals, and it puts that key into the answer key dictionary. Answer key with that key is then replaced with whatever value comes out of the answer key dictionary, which in fact is A, because that corresponds to the key 1. So effectively, this asks whether or not A equals A. A for answer comes from this inner loop, and A for the answer key comes from the answer key. A does equal A, and so we add 1 to David's grade. If the answer hadn't been correct, then we wouldn't have run the inside of this conditional, and David would not have received credit for that question. This continues for each key value pair in David's answer set, and that entire process continues for each individual student inside our student dictionary. At the end of running the outer loop for a given student, we save their grade actually to the exact same dictionary that we created initially, and we do it by creating a new key called grade and giving it the value of their grade. Students grabs that dictionary, student comes from the loop, and it's the current student we're looking at, grade defines a new value in the dictionary, and the variable named grade is the grade that has been computed for that student. Then at the end, I basically start that loop over again iterating over every student in our students dictionary and their answers as the values, and printing out the student's name, the value corresponding to the key grade in their answers dictionary, which as we saw on line 17, was created when we were done calculating each grade. So here, Lugos got 4 right, David got 2 right, and Tara got 5 right. Now if you're a little bit lost, don't worry, this is easily the most complicated code we've covered so far in our course. Take it line by line, and see if you can trace through the way this code actually works.